JEE Advanced 2025, Paper 2, Physics, Question 9. Let us visualize the system. We have a conducting solid sphere of radius r and mass m, carrying a total charge q on its surface. The sphere is rotating about an axis through its center with angular speed omega. We need to find the magnetic dipole moment and compare it with the angular momentum. Let me keep this diagram in the corner for reference. Here is the question. A conducting solid sphere of radius r and mass m carries a charge q. The sphere rotates about an axis through its center with uniform angular speed omega. The ratio of the magnetic dipole moment to the angular momentum about the same axis is given as alpha times q over 2m. We need to find the value of alpha. The key concept here is the gyromagnetic ratio, the ratio of magnetic dipole moment to angular momentum for a rotating charged body. For a conducting sphere, all the charge resides on the surface, but the mass is distributed throughout the volume. This difference in distribution is crucial and leads to a value of alpha different from 1. Let us solve this step by step. Since the sphere is conducting, all charge q sits on the surface at radius r. A uniformly charged spherical shell of charge q and radius r, rotating with angular speed omega, has a magnetic dipole moment equal to 1/3 times q times omega times r squared. This is a standard result derived by integrating over current loops on the shell surface. Let me briefly show why the shell formula is 1/3 q omega r squared. Consider a thin ring element on the shell at angle theta from the axis. The ring has radius r sin theta and carries surface charge sigma times its area element. As the shell rotates, each ring acts as a circular current loop. Integrating the contributions of all such rings from theta equals 0 to pi gives us the factor of 1/3. Now for the angular momentum. The mass m is distributed throughout the entire volume of the solid sphere, not just on the surface. The moment of inertia of a solid sphere about an axis through its center is 2/5 mr squared. Therefore, the angular momentum L equals I times omega, which gives us 2/5 mr squared omega. This is the crucial insight of this problem. The charge is only on the surface, so the magnetic moment uses the shell formula. But the mass fills the entire volume, so the moment of inertia uses the solid sphere formula. This mismatch between charge and mass distributions is what makes alpha not equal to 1. Now let us compute the ratio. Mu over L equals q omega r squared over 3, divided by 2 over 5 mr squared omega. The omega and r squared cancel out. We get q over 3 divided by 2m over 5. This simplifies to 5q over 6m, which we can write as 5/3 times q over 2m. Comparing with the given form alpha times q over 2m, we get alpha equals 5/3, which is approximately 1.667. The answer is alpha equals 5/3, which is approximately 1.667. This falls within the accepted range of 1.65 to 1.67. The key was recognizing that for a conducting sphere, charge sits on the surface while mass fills the volume, giving different factors in the numerator and denominator. Here are some important tips for JEE Advanced. First, always identify whether the charge is on the surface or throughout the volume. Conducting spheres have surface charge only. Second, the gyromagnetic ratio q over 2m holds when charge and mass have identical distributions. When they differ, a correction factor alpha appears. Third, remember the standard results. For a uniformly charged solid sphere rotating with omega, mu equals q omega r squared over 5. For a shell, it is q omega r squared over 3. Fourth, moment of inertia for a solid sphere is 2/5 mr squared, while for a thin shell it is 2/3 mr squared. If you found this helpful, like and subscribe for more JEE Advanced solutions at MAGPIEHUB. See you in the next one.